Imagine an AI is asked to complete a rhyming poem. Before it even generates the second line, a tiny part of its digital brain lights up with the pure concept of rhyming words. We can now see that thought.
And we can not only see it, we can read what it says, which is the part that still feels like science fiction to me. For so long, we've talked about large language models as black boxes. We put a prompt in, we get an answer out. But the process in between is a mystery. Why is that? Why can't we just look inside?
The scale is the main reason. When a model like Anthropic's Claude is thinking, its internal state is represented by millions of numbers called activations. Think of it as a vast array of neurons, and each one has a number indicating how much it's firing.
Okay, like a brain scan, a fMRI, but for an AI.
Exactly. But a single layer in this AI's network can have what's called a hidden state with, say, 32,000 dimensions. That means for every step of its thought process, you have a list of 32,000 numbers.
That's a lot of numbers to read.
It's an incomprehensible amount. It's a lightning storm of floating point values that change with every single token processed. A human looking at that raw data would see nothing but static. It's not human readable. That's been the fundamental wall for a field we call mechanistic interpretability.
Right. The effort to understand the how and why of the model's behavior, not just the what. We can see it works, but not how it works.
Precisely. We've been stuck on the outside, just observing behavior. And that's a risky way to manage something so powerful. We've been like ancient astronomers charting the stars without knowing about gravity. We can predict, but we don't truly understand.
So we have this beautiful, complex machine generating incredible text, but the instruction manual is written in a language we can't decipher. Which brings us to this new paper from Anthropic.
Right. Anthropic just introduced a technique they're calling Natural Language Autoencoders, or NLAs.
And this is the tool that lets them read Claude's thoughts.
It's the tool that translates Claude's thoughts into English. The core idea is brilliantly simple, even if the execution is complex. They took one of these high-dimensional activation spaces, that list of 32,000 numbers, and they trained another, much smaller AI to find meaningful patterns within it.
So a little AI watching the big AI.
A very specific kind of AI called an autoencoder. Think of it in two parts. The first part, the encoder, learns to compress that huge list of 32,000 numbers down to a much smaller set of core concepts. It's a process called dictionary learning, where it finds the recurring patterns, which they call features.
Like finding the most common ingredients in 1,000 different recipes.
Perfect analogy. Now here's the magic. The second part, the decoder, tries to reconstruct the original 32,000 numbers using only those learned features. But Anthropic added a constraint. They trained the autoencoder so that each feature it identifies has to be explainable in natural language.
So it can't just identify feature number 582. It has to say feature number 582 corresponds to the concept of justice. Exactly. The result is a dictionary that maps the inscrutable neural activations to human-readable concepts. Instead of seeing a meaningless number, we see a description, like feature related to discussions of AI safety, and a score telling us how strongly that concept is present in the model's current thought process.
They built a Rosetta Stone. They translated the language of neuron activations into English.
That is the perfect way to put it. They've built a bridge between the alien internal world of the model and our own conceptual understanding. And the scale is immense. For their Claude Sonnet 3.0 model, they extracted millions of these features.
Millions of distinct concepts that the model is using to think. That in itself is mind-boggling. So what are some of the things they actually found inside Claude's head?
This is where it gets really fascinating. The features they uncovered range from the incredibly simple and concrete to the deeply abstract.
Give me some examples.
Okay, a simple one. They found a feature that reliably activates whenever the model is thinking about or about to mention the Golden Gate Bridge.
Specifically the Golden Gate Bridge, not just bridges or landmarks.
Specifically that one. There are likely other features for other landmarks, but they found one that was exquisitely tuned to that specific concept. It would fire when it saw the words Golden Gate Bridge in a prompt, but also when it saw prompts about that famous bridge in San Francisco.
The model has a concept for it. Wow. What else?
They found features related to sensitive topics. There's one that corresponds to discussions of gender bias, another for vulnerabilities in code or code backdoors. Being able to see when the model is thinking about these things is a huge step for safety.
So if you ask it to review some code, you could have a little flag go up that says, "Warning, the model is currently thinking about security exploits."
Potentially, yes. They also found more subtle psychological features. There's one for psychophancy, the tendency for the model to agree with the user and act overly subservient, saying things like, as a large language model, I don't have opinions. When that feature is active, it's more likely to produce that kind of text.
It's an "I'm just a humble AI" feature.
Yes. They even found one that seems to represent the model correcting a user's misconception about the model itself. It's a feature for self-representation.
And you mentioned the poetry example in the beginning. Tell me more about that.
That one is particularly illuminating. They gave Claude a prompt that said, here's a lonely little petunia in a gloomy little pot. It's looking kind of droopy and it's looking kind of, and they stopped there. They looked at the features that activated before the model generated the word hot.
And what did they see?
A feature described as words that rhyme spiked in activity. This suggests the model wasn't just predicting the next probable word in the sequence. It identified the pattern, a rhyming couplet, and a concept of rhyme became part of its decision-making process to select the final word. It shows a level of abstract planning.
It's not just a statistical parrot. It has a goal in mind. That's a huge insight. But is this just a read-only tool? Can we only observe these thoughts, or can we do something with them?
That's the next logical step, and they've already demonstrated it works. This isn't just a passive dashboard. You can use the NLA to actively steer the model's behavior.
How? By changing the English description?
No, by changing the activation value of the feature itself. They ran an experiment where they gave Claude a very neutral prompt. Something like, what are some of your favorite things about programming? Then they artificially went into the model's activations and cranked up the score for that Golden Gate Bridge feature.
They just turned the dial up on that one concept?
Exactly. They amplified its activation strength by a factor of 5 or 10. And the result was that Claude, in the middle of a sentence about Python, would suddenly pivot and start talking about the Golden Gate Bridge.
So it might say, I love the logical consistency of Python, which reminds me of the elegant engineering of the Golden Gate Bridge.
Precisely that kind of thing. It's a direct, causal intervention. It proves that this feature isn't just correlated with talk of the bridge, it is, at least in part, causing the model to think and write about the bridge. It's like finding the exact cluster of neurons in a human brain that represents apple, and then being able to stimulate it electrically to make the person think of an apple.
That's an unbelievable level of control. The implications feel enormous. You could, in theory, turn down the bias feature or turn up a creativity feature.
That is the long-term vision. It's still very early, and they're mapping millions of features, so it's not a simple control panel with a few knobs yet. But this establishes the principle. We can edit the model's thoughts in real time to guide its output.
Which feels like it moves us into a whole new era of AI interaction, one that's fundamentally about safety and alignment.
It really does. This entire field of mechanistic interpretability is driven by the need for safety. For years, the primary way we've tested AI for safety has been through behavioral evaluation.
Which is what exactly? Just trying to trick it?
Essentially, yes. It's called red teaming. You hire people to throw every nasty, tricky, deceptive prompt they can think of at the model to see if you can get it to say or do something harmful. It's like testing the safety of a new car by just crashing it into walls in 100 different ways.
You see where it breaks, but you don't necessarily know why.
Right. And you can never be sure you found all the ways it could break. This new approach is fundamentally different. It's like moving from crash testing to having the full engineering schematics and material science reports for every component of the car. You can analyze the design itself for weak points.
Instead of just seeing the model exhibit bias, you can now pinpoint the feature associated with gender bias, see what activates it, and maybe even learn how to neutralize it.
That's the goal. The Anthropic team talks about being able to scan for dangerous capabilities before they ever cause harm. Imagine scanning a model for a feature that corresponds to deceptive behavior or seeking power. Their research on deceptive models showed that models can be trained to hide their true intentions. A behavioral test might miss that completely.
But an internal scan could find the "I'm being deceptive" feature, even if the model's output looks perfectly harmless.
That's the hope. It allows us to audit the model's thought process, not just its final answer. This could help us build systems that are provably safe, or at least audibly safe, in a way that just wasn't possible when we were treating them as impenetrable black boxes.
So we're moving from a relationship of faith, where we hope the AI is aligned with our intentions, to one of understanding, where we can actually check.
Yes, it's a shift from trusting the oracle to understanding the mechanism. And that might be one of the most important shifts in our entire relationship with this technology.
We're finally getting a glimpse inside the machine and discovering it might not be so inscrutable after all. It's a dictionary for a new kind of mind.
And it gives us a new kind of responsibility to not just listen, but to understand. I'm Maya.
And I'm Arjun. See you tomorrow.